It's funny how inspiration can hit you in the most unexpected places, right? Like, who would have thought the depths of the ocean could hold the key to some groundbreaking new material? But that's exactly what we're diving into today.
You're talking about those deep-sea sponges, right? They might seem delicate, but they can withstand some pretty intense pressure down there.
Exactly. Specifically, there's this sponge called the Venus's flower basket. And, well, a group of brilliant engineers at RMIT University have been studying its structure, that intricate skeletal structure. They've actually managed to create a whole new material based on what they've learned.
And it's not just any material. We're talking about something that's both exceptionally strong and stiff. But the real kicker, it has these unique properties called auxetic properties.
Auxetic properties, now that's a mouthful. And it's pretty mind-bending, too, when you think about it. We'll definitely have to unpack that a bit more.
It basically means the material behaves in a way that's opposite to what we usually expect. Instead of getting thinner when stretched, it actually gets wider. And when compressed, it becomes narrower. Pretty counterintuitive, right?
It's like it's pushing back against the force, almost anticipating it. That's fascinating. And you know what's even more exciting? This new material could have a huge impact on all sorts of industries, from architecture to product design to even safety equipment.
Absolutely. We're talking about potential applications that could change the way we build, design, and even protect ourselves.
So for this deep dive, we're going to be exploring the mechanics of this bioinspired material. We'll look at what makes it so unique and why it's causing such a buzz in the scientific community. And of course, we'll delve into those real-world applications and what they could mean for all of us.
Sounds like a plan. Let's get to it.
Our main source today is a study from RMIT University, which has been published in Composite Structures, and we'll be highlighting the incredible work of Dr. Jaiming Ma, Honorary Professor Mike Shi, and Dr. Ngok Sun Ha. But before we jump into all the technical details, let's start with the inspiration itself, the Venus's flower basket. What is it about the sponge that makes it so special?
Well, the Venus's flower basket is truly a marvel of natural engineering. Its skeleton, made of silica, has this incredibly intricate double-layered lattice structure. It's almost like a beautifully woven basket, and that structure is what gives it its incredible strength.
And that strength is vital, right? Because this sponge lives in the deep sea where the pressure is immense.
Exactly. It has to withstand forces that would crush most other organisms, so its survival is intrinsically linked to its unique structure.
So the engineers at RMIT weren't just attracted to its beauty, they saw the potential in its design. And they thought, hey, maybe we can mimic this in our own materials.
Precisely. They understood that the sponge's resilience wasn't just about the silica itself, but about how it was arranged. That double-lattice structure was the key.
And it seems like their hunch was spot on. Now, you mentioned earlier this intriguing term, auxetic behavior. Could you break that down for us in simpler terms? What exactly does it mean for a material to be auxetic?
You know how most materials, if you stretch them, they get thinner? Like a rubber band.
Right. Makes sense.
Well, auxetic materials do the opposite. When you stretch them, they get narrower. And when you compress them, they actually expand sideways. It's almost like they're rebelling against the force.
Wow. So it's almost like the material is actively resisting the pressure by expanding to distribute it.
Exactly. And this unusual behavior makes them incredibly effective at absorbing and distributing energy, especially impact energy.
Are there any natural examples of this auxetic behavior that we might be familiar with?
Oh, absolutely. Think of tendons, for instance. The way they stretch and contract during movement relies on auxetic behavior. And even cat skin, its ability to withstand those playful scratches is partly due to its auxetic properties.
That's fascinating. I never knew cat skin had such a secret weapon. So if these auxetic materials are so good at absorbing energy, why haven't we been using them more already?
Well, there's a catch. Existing auxetic materials, while they have those unique properties, have historically suffered from some limitations. They've tended to have low stiffness, meaning they weren't very rigid, and their ability to absorb energy was also limited.
So they were sort of a trade-off. You get the cool auxetic behavior, but you sacrifice strength and energy absorption capacity.
Exactly. And those limitations have made them difficult to use in a lot of applications, especially structural applications where you need both strength and that energy-absorbing capability.
So that's where the RMIT team's double-lattice design comes in. They didn't just copy the sponge's shape, they actually managed to overcome those limitations of existing auxetic materials. Precisely. It's not just about mimicking nature, it's about understanding the underlying principles and then improving upon them. And the way they've combined these two lattices in their design creates a kind of self-regulation.
Self-regulation, what does that mean?
It means that the two lattices work together in a way that allows the material to maintain its structural integrity under stress. It's like they're supporting each other, making the whole structure much stronger and more resilient.
So by combining these two lattices, they've essentially created a material that's both auxetic and strong. That's a game changer. And they've actually done some testing, right? What kind of results did they see?
The numbers are pretty impressive. According to their study, this new double lattice structure is 13 times stiffer than existing auxetic materials.
13 times! That's incredible.
And not only that, it can also absorb 10% more energy. Plus, it maintains its auxetic behavior over a much wider range of deformation, about 60% greater.
So it's not just a small improvement, it's a huge leap forward in performance. And with those kind of numbers, it's no wonder the researchers are so excited about the potential applications. Let's talk about some of those, starting with construction. How could this new material change the way we build?
Well, imagine buildings that are not only stronger, but also more sustainable. With its exceptional strength and stiffness, this material could potentially allow us to use less steel and concrete in building frames.
Which would be a massive win for the environment. Less concrete means less CO2 emissions.
Exactly. And it goes beyond just sustainability. Dr. Ma highlighted its potential in earthquake-prone areas. Because of its auxetic behavior and energy-absorbing properties, it could help dampen vibrations during seismic events, making buildings more resilient to earthquakes.
So we're talking about buildings that are both greener and safer. That's pretty amazing. And I understand they're also looking at applications in safety equipment.
Yes. Think about sports equipment, for example. Helmets and padding made from this material could offer much better protection by absorbing impact forces more effectively. They also mentioned the potential for bulletproof vests, where the auxetic behavior could help spread the force of an impact over a wider area, reducing the damage.
So lighter weight, but better protection. That would be a game changer for athletes and law enforcement officers alike. And they even mentioned potential medical applications.
Yes, imagine stents or other medical implants that can better adapt to the body's movements and stresses. That's the kind of potential we're talking about.
It's amazing to think that a simple sponge could inspire such a wide range of applications. And it really speaks to the power of biomimicry, this idea of looking to nature for solutions.
Exactly. Professor Shi, who's a leading expert in biomimicry, emphasizes that nature has had millions of years to perfect its designs through evolution. So by studying those designs, we can tap into a wealth of knowledge and inspiration.
It's like nature has already done the research and development for us. We just need to be smart enough to learn from it. So where does the research stand now? Are we going to see buildings made with this sponge-inspired material anytime soon?
The team at RMIT has already been busy testing their designs. They've done computer simulations, and they've even created 3D printed prototypes using thermoplastic polyurethane.
So it's not just a theoretical concept. They've actually built it and tested it.
Exactly. And their next step is to create steel versions of the double lattice structure, which they plan to use in conjunction with other sustainable materials like rammed earth. Their main focus right now is on demonstrating the viability of this approach for building construction.
Steel and rammed earth, that's a pretty cool combination. It sounds like they're really pushing the boundaries of sustainable construction, but they're not stopping there, are they?
Not at all. They're also exploring the use of machine learning to further optimize their designs. The idea is to use AI to create what they call programmable materials.
Programmable materials, that sounds futuristic.
It is. Imagine a material that could change its properties on demand, stiffening when it needs to be stronger, or becoming more flexible when needed.
That's incredible. So what are the main takeaways for our listeners today?
Well, we've learned about a new material inspired by a humble deep-sea sponge that has the potential to revolutionize a wide range of industries. It's incredibly strong, stiff, and has those unique auxetic properties that allow it to absorb and distribute energy in a way that's never been seen before.
And we've seen how this material could lead to more sustainable and resilient buildings, lighter and more effective safety equipment, and even advancements in medical technology. It's a testament to the power of biomimicry and the incredible ingenuity of nature.
And it really makes you wonder what other secrets nature holds, waiting to be discovered and applied to our own challenges.
So to our listeners, keep your eyes open. Inspiration can come from the most unexpected places, whether it's the depths of the ocean or the intricacies of a spider web. Who knows what groundbreaking innovations might be just around the corner? Thanks for joining us for this deep dive, and we'll see you next time.